I, I thank the committee for being here. I just want to say that uh, my hope for Myrtle as a student was that he would teach an old dog new tricks. Uh, it was clear there's a revolution going on in AI and AI for robotics. And I need help, I needed help keeping track of what's going on. He's done an excellent job teaching me, and as I say, trying to teach an old dog new tricks, which people say is impossible. There you go. All right.
Thank you so much, Chris. Thank you everyone for coming to my thesis talk on strategies for robot learning from human data. My name is Mrinal. We have our wonderful committee here. So Chris, my advisor, Dave, Oliver, and then we have Rutha on Zoom, who can see everyone through the owl. Oh, am I gonna reset this? Make sure that works. And then go there. Perfect. Okay, we have been striving towards general purpose home robots for a long time now in the field of robotics. And many other adjacent fields in AI have seen really great success with general purpose models that work in the wild. People can pick up these models and use them for their own purposes in a lot of cases. And so while we've seen a lot of really impressive work in robotics, including some of this stuff here, we haven't quite yet made enough progress to achieve this level of capability that we want. There's a lot of things we will want from, oh, that skipped a slide, hold on. There's a lot of things we want from useful home robots. They should possess diverse skills that let them interact with a wide variety of objects. So these are some videos from a study we did on learning cooking skills from human video. They should be able to learn from experience and autonomously improve their own performance with minimal human supervision. So these are some videos from some work we did on learning reward signals from human video and then optimizing that on a robot with reinforcement learning. And finally, they should be capable of providing useful assistance to humans on a variety of common household tasks in very unstructured environments. So this video comes from a study we did where we put a vision language model task planner on some smart glasses, and we tasked it with helping people through everyday cooking tasks. Robot learning has promised to deliver these capabilities for us by drastically reducing the amount of effort we need to teach robots new tasks. But it's very generally accepted in our field that robot learning is fundamentally data limited. These are two very large-scale data collection efforts that the academic community has gone through recently. Aloha 2 used 35 operators with 10 robots across 8 months, and Droid used 50 operators with 18 robots across a year. And so these are pretty large scale in terms of the academic context. And Droid, I think, collected about 350 hours of data. But when we look at human data can help us drastically reduce the amount of robot data we need to deliver on these capabilities and learn new tasks. Human video data exists at scales that are an order of magnitude higher than our robot data sets. This is Ego4D on the left, which some folks consider old by now, but it has 3,600 hours of data. This data features a lot of very common household tasks that we want our robots to perform and has a large diversity of environments and objects. Human language data has also been very nicely encoded for us in large language models. To some extent, these models have read the entire internet, and they have very good priors on human tasks and environments. Unfortunately, human data also comes with a lot of challenges to making it work well for robotics. First of all, human data is ungrounded. Even our richest representations of human data, like video, are missing very important sensory signals like joint efforts, contacts, forces that would be invaluable for robot learning. This is not doing what I want to do. Perfect. Human data also contains very large embodiment and environment gaps. Human data contains environments and agents that our robots have never seen before, and so we have to transfer across a very large distribution shift. And finally, humans are unpredictable. Humans act according to their own reward function or incentives that are not transparent to a robot. Sometimes these incentives aren't even transparent to humans. So a robot learning from a human must be able to understand what information human data is relevant to its domain. I think it's also important to note that human data comes in a wide variety of representations. So here I've laid out these representations on two axes. Richness is how much information is actually encoded in that representation, and abstraction is how compressed the information is, or the ratio of useful information to what we might consider noise. And so I think we can exploit these very diverse representations of human data to help overcome some of the challenges that are associated with human data and more effectively use it to enable capabilities we want from our robots. So to do this, my thesis has looked at three key questions. What are appropriate features and representations in human data? How do we identify these features? And how do we use them to close the robot data gap? And to illustrate the importance of considering representations and to highlight the gap that I think still exists between our current implementations that use human data and the robot capabilities we want, let's take a very quick look at one of the most popular ways of using human data right now, which is the Vision Language Action Model, or VLA approach. So we're going to start with a pre-trained LLM, and this LLM reasons in the high-level language space and can respond to language queries. And to that, we're going to attach a vision encoder, and then we'll fine-tune the whole new model to process both vision and language queries. So this model is going to map images into a high-level language reasoning space to reason about them. And now we'll tack on an action head, and we'll fine-tune this new model with robot actions. So this approach is very convenient. It allows us to use a lot of different human data in one model. We can use image data to train the video encoder, language data to train the language model, vision language data to train the VLM, and even some new VLAs are using human video data to train the full pipeline as well. But let's really quickly follow the path of inputs through this model. So this time, instead of richness, I've got processing on the x-axis, which tracks as we kind of process this data. So we're going to start with visual and textual inputs, and we're going to map them up to a high-level language abstraction space, and then we're going to map them back down to low-level robot actions. Is this a problem? Well, there's been lots of really good work on studying how well VLAs retain some of the general use properties that their vision language model backbones have. These studies have found that many VLAs are sensitive to slight changes in prompts, in background, or in objects, which doesn't quite deliver the general properties that we want from these models. And newer VLAs have certainly addressed some of these limitations, but not all. Furthermore, the VLAs that do leverage human video, they often need large amounts of both robot data and then paired robot data and in-domain human data to help align these human and robot representations well. So that's still a pretty large data cost for us. So I think we can use human data more effectively to reduce the amount of robot data we need by being cognizant about how appropriate different representations of human data are to different robotics problems. And in my thesis work, I've explored what I'll call a general recipe to reason about representations of human data. The components of this recipe are, I gotta make this bigger. Analyze deployed robot learning systems that have been augmented with human data. Identify appropriate features and representations in human data for a given robotic subproblem. And integrate models built with these representations into existing robot learning and reasoning paradigms. And I've explored these strategies in two domains that I think are very crucial for building generally capable home robotics, which are task planning and skill learning. In both these domains, I've studied learning systems that use human data on realistic tasks. I've identified which features and representations I believe to be most effective from these studies. And I've integrated models built with these representations into existing paradigms. This figure is an overview of a lot of my thesis work, and so I'm going to refer back to it as we go through the work I've done. With that, I think I should lay out how the rest of this talk is going to go. So we're going to first talk about some of my work on task planning with vision language models, and we'll look at some of the challenges in this area. We'll talk about a user study I did to identify some of those challenges, as well as what features I think are really good. We'll look at related work and how some other folks have tried to address these challenges, and we'll talk about some of the work I've done on better grounding vision language models to their environment. Then we'll take a look at some work I've done on skill learning from human video. We'll talk about what other folks have done in this area. We'll talk about why I think visual motion features are really effective for this domain and how I know that from the cooking skill study. And then we'll talk about some work I've done on learning dense reward functions from human video. And then we'll wrap up with some conclusions and some future work. So let's dive into task planning with vision language models. Task planning concerns the problem of predicting a set of high-level actions to solve a given task. And since 2022, we've seen really good promise in the ability of vision language models to enable very general task planning for us. These models, as we said, encode a lot of information about human tasks and environments that would take us ages to collect if we were running a robot. There are some significant challenges with VLMs for task planning. First of all, VLM planners struggle to process large amounts of visual information. This phenomenon is sometimes referred to as context rot, where if we add additional irrelevant information into the input of a LLM, even if we have the same amount of relevant information, the overall performance will go down significantly. And this phenomenon is inherent to LLMs and to some extent to transformers in generally, and it's been documented in many domains. VLM planners also over-index on visual information, which on its surface seems contradictory to the point I just made, so let's dive a little bit deeper. Here's the performance of an LLM planner on Alfred, which is a very popular task planning benchmark. And then here's what happens if I add the current task image into the prompt without changing anything else. We see a reduction in performance, which seems a little bit weird. So when we train VLMs make a core assumption that any visual input they get is always relevant to their processing. And like I said, this assumption is engendered by their training. When we fine-tune a vision language model with paired vision language data, we only give it vision data if we expect it to reason about it. So as a result, when a VLM gets an image input, it directs a lot of its internal attention to that image. This assumption works great when humans query VLMs because I follow that same assumption. I'm only going to give an image if I expect it to reason about it. But when we use VLMs as an agent operating in an environment by itself, it's going to see a lot of visual information that's not necessarily relevant to its task. But if it over-indexes on that visual information, it may do so to the detriment of any textual information that lives in the prompt, and we'll see a reduction in performance if we needed that information to construct good plans. So as a result, we can say that VLM planners struggle to adequately condition their plans on visual information from the environment. And this claim comes from a first of its kind study that we did. Back in 2023, we wanted to assess how well do VLM task planners perform on realistic tasks. And at that point, people have done a lot of work on VLM task planning, but it'd been in kind of clean environments with limited action spaces. So we deployed a set of VLM task planners on a pair of smart glasses. These glasses would observe video from an egocentric camera and predict steps to complete 3 different cooking tasks in a busy office kitchen. And then to remove the physical execution capabilities as a factor, I bullied 18 different people in the Meta office to do a user study with me where they had to wear these glasses and they had to follow the steps that the VLM would tell them to do to try and complete these cooking tasks. So this is my friend Jessica trying to make a latte while the LLM whispers in her ear. We tested 2 different approaches to building VLMs. Socratic models will convert vision to text with pre-specified prompts. So these models will explicitly represent vision as textual details. Visually conditioned language models, or VCLMs, are the more popular way of building VLMs, and these will embed vision using a pre-trained vision encoder. So these models will implicitly represent visual information in a learned latent space. Across a lot of offline benchmarks and the online study that I just showed you, we found that consistently Socratic models that explicitly represent visual information as textual details outperformed VCLMs that implicitly represent visual information as latent representations. And it's important to note here also, we gave the VCLM access to the same textual details that the Socratic model was using, and its performance went down. So this further backs up our claim that VLMs can over-index on visual information when using them for task planning. Also, to better understand kind of where our errors came from, we did a detailed error breakdown. We classified errors into 2 types. Grounding errors occur when the VLM predicts an action that has already been completed or an action for a different version of the task, indicating it hasn't adequately grounded to the environment. And planning errors occur when the VLM predicts something out of order or for an irrelevant task. And we see that the large majority of our errors are grounding errors, and this were true across all the tasks we tried and all the models we looked at. So, yes, Oliver. Yes, thank you. So in our study, we would basically have the human do a couple different actions any way they wanted first to kind of randomize what the task state would be, so we weren't controlling that. So that's what's going on in blue. And then from there, after the dashed line, this is when the VLM takes over and starts predicting actions. And so green actions are predictions that it took that we determined to be correct. Yellow actions are predictions it took that we determined to be optional. They're not necessary for the task state, but they're not wrong. And then the red and purple actions are ones we classified as errors. Does that answer your question?
I think so. So like you got like steam milk in the middle ones was how can I do that next? You should do it again and you should then add the milk.
Yes.
Okay. And like the first one, if you pull the shot, then that's the error, and then you add. Okay.
Yeah. So if it tells you to pull a shot again after you've already pulled a shot, that's an error. It shouldn't do that.
And all converge together at the end there because those are the successful.
Yeah, those are a lot of the ones where we've come to a successful state. And so the stars represent, and sometimes we've reached successful states along the way, but then after that's a matter of preference, whether you want sugar in your latte or not. So that is where we kind of get to optional actions. Cool. I talked about this in my proposal, so I didn't spend too much time here going over this, but we can chat more about it too later. Okay, so in addition to informing our ideas about what the limitations of VLM planners are, I think this study really clearly shows us that representing visual details as text is more effective than implicit visual representations for VLM task planning. So let's check back in with our strategies and our map. We study task planning systems that use human data in the form of VLMs, and we've identified that representing visual details as text is an effective feature. So let's look at how to address some of the limitations we saw now. We have the following desiderata for an effective VLM planner. First, it should be able to extract specific visual information and represent it as textual details. Second, it should only use vision when necessary. And third, we should identify relevant visual information and discard everything else. So I think it's a good time to look at how some prior work on multimodal LLM reasoning as planning has tried to meet these same criteria and solve this problem. One of the most straightforward approaches is what I'll call direct grounding, where we just rely on the VLM vision encoder to represent visual information in a way that's useful for reasoning or planning. And this is the approach that a lot of VLAs have taken. Next, we have grounding with vision APIs, where we provide the model with a set of vision APIs like object detectors or segmentation models that can call, and it'll construct a plan and then use these vision APIs along the way to pull out information as it goes. And the last one is what I'll call dynamic reasoning with visual queries. So this approach will modify its behavior during planning or reasoning based on the results that come back from visual queries. And these can be vision APIs or the innate vision capabilities of the model, but the important part here is it dynamically adjusts its reasoning. These approaches can be very powerful and very effective, but they can be challenging to get right because VLMs have a very large reasoning space. So from this related work, we also saw that a really great freeform way to pull out visual information as text is visual question answering, which we can do for videos. This uses a two-step process. In the first step, we're going to localize appropriate frames by looking through the whole video and seeing how well a frame can answer a question. And then in the second step, using those appropriate frames we identified, we're going to actually answer that question. And we like this for two big reasons. One is that it lets us search very long video history for visual details. And second is that it makes this visual history queryable with text, which is very beneficial to us as well when working with language models. Okay, so this addresses the first of our desiderata, which is to extract specific visual information and represent as textual details. How do we go about the second two? So to meet our other two, we can discuss how language models actually construct plans. And one way to do it is with text generation, where we take in the task description and a set of prior actions, and we're going to output next actions that we think will solve the task as text. We can also use language models to reason about a set of actions, though, and I think this is really interesting. So if we look under the hood, we can use LLM log probabilities to give us a probability distribution across next actions. And importantly, if we were to add extra textual information into the prompt, we can see that these probabilities may change. They may update based on this new information. So we could use this to our advantage. We consider this probability distribution to be our belief state over next actions. So we have an initial prior belief state, and then after adding a new textual detail, we have a posterior belief state. We can compute the entropy of each of these belief states using the discrete entropy equation. So here, P of X is going to be each of these discrete probabilities. And then we'll borrow some ideas from information theory. We compute the task-relevant information gain as the difference between prior and posterior belief space entropy. And I'm going to say this is task-relevant because we're using the belief state across next actions. So if we get information that isn't relevant to choosing the next action, it should not change the probabilities and therefore should not create any information gain. So let's build a reasoning pipeline around this insight. Every time the LLM has to make a decision about next actions, we're going to compute our belief state probability distribution. If we're sufficiently confident about a single action, we can just select that action and move on. But if we're not sufficiently confident, we'll record our prior belief space entropy. And then we'll ask the LLM to generate a set of disambiguating questions that can help it decide among these possible next actions. We can answer these questions with visual question answering and our task visual history to generate a set of textual details that may be relevant. For each of these details, we'll calculate the posterior entropy that it creates when we add it into the LLM prompt. And then with all these prior and posterior entropies, we can compute the information gain associated with each textual detail. So we'll just pick the best positive one, and we'll add it back into the prompt and repeat until we are sufficiently confident about our planning. So this addresses the other two things that we want. We can now only use vision when necessary, and we now identify relevant visual information and discard everything else. So first, let's take a look at the performance of this approach on the Alfred benchmark. This is a very popular benchmark in task planning. It's got 7 different types of tasks, and they've scaled it up pretty nicely. They've got 84 different objects and 120 different scenes. So I think all in all, there's about 1,500 like task instances in the validation set. And so we called our method query, and using it, we do see some slight improvements on the Alfred benchmark. Alfred is a huge task planning benchmark, but it's not really great to stress visual grounding, which I think is why we see only mild improvements here. This setting actually gives the planners access to ground truth information about objects in the scene, which kind of further reduces the burden on visual grounding. But importantly, we can now selectively attend to vision without reducing our performance. And I'll also note that these results come from Qwen 3 vision language 8 billion parameters, which as a few months ago was the best VLM I could fit in my GPU. And so even with modern VLMs, we still see this issue where natively adding in vision will cause it to over-index on that visual input and reduce performance. So this is a phenomenon consistent across VLMs for the last 3-4 years. Okay, so to better stress visual grounding for task planning, we made a benchmark in the same simulator that Alfred uses. So we record video of various cooking tasks, and we annotate the video with corresponding simulator actions. So that way we could sync the simulator state to the task state in the video, and then ask the robot to plan from there with only access to the visual task history. So the robot has to determine task state and predict future actions without access to kind of ground truth information. This benchmark used 7 different tasks with 5 different environments, and we ran each run 5 times to try and mitigate the randomness that comes out with VLM planners. So we tested a couple different baselines here. We looked at the same Socratic baseline from our real user study, but now applied to this benchmark. We also looked at 2 different variants of React, which is a popular LLM iterative reasoning framework. VQA React uses our same VQA process to extract details, and MM React is multimodal React, which gets vision APIs to try and extract details. We looked at 2 ablations of our method as well. So the VQA only method does the same kind of question generation and question answering, but then it doesn't use information gain to sort among the questions, just puts them all into the prompt. And self-evaluation replaced our information gain metric with LLM self-evaluation, which has been somewhat popular, where we ask the LLM to reason about whether a specific visual detail is relevant for its planning problem. So we see that generally query outperforms a lot of the other baselines. And we see bigger gaps at longer planning horizons. We looked at horizons from 1 to 5, where a horizon is the number of actions we expect to be left in the task. So we generally saw bigger gaps at longer planning horizons, which is good for planning. Also important to note that we outperformed both of these ablations, which kind of stresses the importance of not only having a good form of self-evaluation in the form of information gain, but that information gain was better than prior work on self-evaluation, at least in this context. Finally, we tried to do some hardware tests as well with query on a bimanual system where we wanted to make a sandwich for us. So we'd looked at 3 different kind of sandwich making tasks with 3 runs each across our different methods. And we looked at both success rate and efficiency, where efficiency is the number of actions that actually progress the task state divided by the total number of actions that the planner took. So we saw that query makes some performance improvements here, but we are kind of limited by the quality of our skills for actually trying to manipulate these objects and make a sandwich. Okay, so coming back to our strategies, we identified that visual details as text was a good representation for our task planning problem. And we leveraged this by building a system that could reason about information gain to decide which visual details were relevant for task planning. I think there's 2 important takeaways from this work. First of all, as I've been saying, is that representing visual information as discrete textual details is very effective. But we've also been discussing a lot kind of in the LLM research folks about how to enable LLMs to effectively evaluate their own output and improve their performance. And I think one of my takeaways here is that adding some type of structure, which in this case was reasoning about information gain, leads to better self-evaluation. Okay, so now let's move on to some work about robot skill learning from human video. So skill learning is the other very important component to enabling a kind of general home robot. And we want to think about how we can use human video to reduce the amount of robot data that we would need to teach a robot new skills. It's a So human video is a very rich source of supervision for learning robot skills, and there's a lot of folks who have looked at how to do this. One popular approach right now is to use human video as additional data inside VLAs and world models. This approach generally needs in-domain human data, like I said, which is human data collected in that same environment on the same tasks, and uses quite a bit of robot data to try and align these human and robot representations. Though there's some really good work from Iki, one of my collaborators, who showed that you can align this data from diverse embodiments, including humans and robots, by representing actions with visual motion features like optic flow. So that's very cool. The next category is direct imitation, which attempts to directly imitate actions from human video. This comes in two varieties: agent imitation, where we try and retarget human actions we see in the video to robot actions and then learn that way, and object imitation, where we try and predict object trajectories and then solve for a set of robot actions that will enact those trajectories. These can work well, but they sometimes struggle with contact-rich tasks, and they often need a lot of extra robot data to kind of make up that performance gap. Finally, there's a work on learning rewards from human data and using reinforcement learning to optimize those reward functions on a robot. And I think this work is really promising. Reinforcement learning, when done well, can help us cross this human data to robot gap. And it's because a robot can learn to optimize a reward function on its own embodiment using the state distribution that it's likely to see. These works often use a form of contrastive learning to learn a value function that estimates distance between an observation and the goal. So they've kind of learned this distance function as a reward. And we've seen some of these folks do online robot reinforcement learning, leveraging rewards from in-domain human data. And then there's actually been some cool work that looked at doing offline RL with rewards learned from in the wild data. But to the best of my knowledge, we haven't seen too many folks look at kind of getting to online RL with in the wild human data to learn reward functions. And this is important because online RL is generally more performative than offline RL for teaching robots these kinds of tasks. Okay, so unlike a lot of this prior reward learning work that uses contrastive learning to estimate rewards, I'm going to argue that visual motion features are more effective for learning robot supervision signals than contrastive methods that learn distance functions. And I'm going to argue this because we did a study on the relative efficacy of various representations of human data as reward signals for robot skill learning. So this study was fairly straightforward. We had a library of various position force controllers, and we tested how well various human data representations could select among this library to accomplish 16 different cooking skills. So we tested 3 different representations to select behaviors with language. We use the same LLM capabilities I showed off for task planning. We give the LLM a description of the task we want, and we ask it to reason about automatically generated descriptions of the controllers and how well they might suit the skill we want to execute. We also looked at selecting behaviors using popular off-the-shelf video encoders. These encoders are also trained with contrastive learning on kind of classification tasks, and they should map videos with similar actions to close together in this latent space. So here we collect videos of the robot using different controllers to attempt a task, and we compare them to a human video demonstration by measuring cosine similarity in this latent space. And the last one we looked at was selecting behaviors using by encoding visual motion features. So we use an off-the-shelf model to extract optic flow from the same videos we looked at for the previous one. And then we trained a flow encoder to generate discrete flow features that would characterize the types of flow it saw in that video. So we'd aggregate these across the video into a histogram, and then we'd use histogram distance metrics to measure the similarity between the videos. Yeah, Dave.
Sorry. So for the second and third model, you're using contrastive learning to train them?
The video the video encoder comes pre-trained with the contrastive thing. That's Lavila. They've done kind of vision language contrastive. For ours, we looked at a lot of the kind of self-supervision methods for learning. And a lot of them kind of make assumptions that are specific to RGB images and don't work well with flow images. So at the end, we actually just trained a VQ-VAE, and that's kind of where we get these discrete flow features. And we found that just by kind of amalgamating them across the whole video, we get this histogram that works reasonably well. I went down a whole rabbit hole on trying to make like SimClear and SimCiam work for optic flow maps, and it didn't really give me the results I wanted.
Okay, so you didn't actually use like VIP or time contrasted networks or anything like?
Not for this one. We'll get to that in a second.
Oh.
Yeah, that's in the next work. This would have been done. I think this started this project around the same time that maybe VIP had just come out. So I had like read the paper, but I hadn't really messed around with their stuff
Okay,
yet.
I guess you should have presented like previously, you're like.
Yeah, I'm
Networks that don't work.
I'm backing up for a quick second here to talk about why I'm arguing for visual motion features, and then we'll talk more about directly comparing to actual contrastive methods.
Okay.
Yeah.
All right.
Thank you, Dave. Okay, so these are 3 different representations, and when we look at them on the performance of different cooking tasks, we found that, LLMs do okay, they can do some reasoning, but importantly, I believe that visual motion features from our flow encoder significantly outperform the contrastive distance features from the video encoder. I think this is also important because we trained our flow encoder with an order of magnitude less data, human data, than the video encoders used when they were trained. Okay, so let's come back to our overview. We studied the efficacy of different representations of human data to supervise robot skill learning. And we identified that visual motion features seem to be an effective representation. But what we've built so far is essentially a sparse reward function, which only gives us feedback at the end of a robot episode. I want to use visual motion features to build a dense reward function that will give us per step feedback, because it's certainly much more effective for robot policy learning. So now we'll get to this. As I mentioned, there's been some really good prior work here that looked at learning dense reward functions from human video. And this specifically is VIP, which is kind of emblematic of this class of what I'll call temporal distance reward methods. And they have really good code and models, and they've been trained on the same human video data that we want to use. So they're going to measure the value of an observation as its temporal distance to the goal, or the number of frames between it and the final frame of the video. And they're going to use contrastive learning to learn an image encoder that maps these images to a latent representation that tries to preserve this distance metric. And so if you use this image encoder along with a goal image, you should get a reward signal that looks something like this. And it seems to work reasonably well. There are a couple limitations with the temporal distance approach. First of all, this value function has to be transferred to out of distribution images, where we've now replaced a human arm with a robot arm, and we might be seeing environments and objects that we've never seen before. Second, these human videos only contain successful demos, and this approach is nothing to explicitly try and mitigate false positives, where the robot may take actions that are similar to the human, not achieve the same outcome, but be rewarded anyway. And finally, human video is unstructured. Hesitations can negatively bias previous frames. So if the human hesitates for k frames in the middle of the execution, then that will subtract a value of k from all previous value estimates in that video. Okay, so how do we address these limitations with visual motion features? When I was looking at this, we found that actually we've seen really good performance from dense point tracking models, which are similar to optic flow, but we found they work better for our domain. These models can accurately track objects in varied scenes, and they generally perform better. So we went that route. And we're not the first people to look at this. There's been a bunch of really good work that looks at predicting point tracks as an action representation. But instead, I want to use it as a reward representation to predict rewards. So my idea here is if we can learn to predict how we expect points to move for a given task by training on human videos, and then we compare our predictions to how we actually observe points moving in a robot episode, we can generate a reward signal based on the alignment between the predicted motion and the observed motion. So how do we train a motion prediction model like this? We're going to design a pipeline that takes in egocentric human task videos, and we'll use some off-the-shelf models to grab masks of task-relevant objects. And we'll use our point tracking models to track points across these videos. Then to train our model, we take in an observation, the object mask, and a set of query points, and we just want to predict how these points are going to move in the next frame, which is very easy to train via regression. To use this model to compute rewards, we're going to pass an episode of robot behavior to our motion prediction model, and we'll predict what we expect the point motion to be in each frame. Then we'll track points across the entire robot episode. And again, we can measure the alignment between our predicted point motion and our observed point motion at each frame to generate this dense reward function that we want. The last step of this process is that we need to make a reinforcement learning algorithm that can optimize a policy on the robot to maximize this reward function. And because RL, when done from scratch, can be very slow, we want a method that allows us to initialize the policy with a very small set of demonstrations. There's been some really great work in this area. So RLPD identified a set of design decisions that make off-policy RL, like soft actor critic, work really well with demonstrations. ResIP looked at doing residual RL that lets us use very powerful behavior cloning methods like diffusion policies to learn a base policy and then learns residual corrections to that policy. And then ResIP looked at doing residual RL with some, ResFit looked at doing residual RL with some of the insights from RLPD, and they show that you can make this run on a humanoid, which is very cool. So we draw very heavily from these methods when we design our own reinforcement learning pipeline here. So to learn a policy that optimizes this reward function on the robot, we'll start by collecting a very small demo data set, which we call the offline data set. So in our work, this was only 10 demos and takes about 5 minutes to collect. We'll couple this with the online buffer that's going to hold the robot data that it collects as it learns and explores. And we'll label both these buffers with the reward from our model. So to train a policy, we're first going to start by training this base policy with the data in the offline data set. So that's just behavior cloning. And then during reinforcement learning, we're going to freeze that base policy and only learn a residual policy to apply corrections. So we're using soft actor critic with the modifications that RLPD identified, plus some of our own. Obviously, a lot of parameter tuning goes into reinforcement learning. But this residual policy will leverage both our offline data set and the online buffer to learn fairly quickly and stably. So this is the result. This is online reinforcement learning on a real robot hardware with a reward function learned from internet scale human video. I looked at 3 different tasks. We looked at opening a microwave, folding a towel, and wiping coffee grounds off the counter. Each of these training runs was 100 episodes of robot interaction, which took about an hour to an hour and a half of wall clock time, and that included both environment interaction, reward computation, and policy updates. And I want to stress, compared to having to collect a lot of additional data to improve robot performance, I barely did anything here. I did while this trained, I did crosswords on my phone. I called my parents. I listened to a podcast. I just hung out, and occasionally I reset the environment while the robot learned itself. So we call this approach MPR for motion prediction reward. And when we compare it to VIP, we see that not only does it reliably improve over the performance of a base policy, but we significantly outperform VIP in this online RL setting. We can understand part of why this is by looking at reward signals from these different methods on some demos from simulation. So MPR very closely tracks a hand design reward function and shows a lot less bias in the reward signal than VIP does. There's also a little bit more to the story. So this plot shows some of the success rates during training as we train in a sliding window of 20 episodes. So this is for MPR in blue and for VIP in orange. And so VIP actually can learn, but it doesn't do so very stably, and it sometimes forgets what it has learned, which can slow down RL training. And to understand why, we looked at the reward signals and the value functions that are learned after RL on a successful episode on the left and a failed episode on the right. So in the successful episode on the left, the robot grabs the handle of the microwave and opens it, and clearly both reward functions recognize that this is successful, and the value functions learned after RL reflect this as well. In the failed episode on the right, the robot reaches for the handle, but misses and pulls back anyway. And so we see that VIP actually still assigns this episode some reward, which is a false positive. The robot went through the motions, but didn't achieve the outcome we wanted. MPR assigns this episode no reward. It says the objects didn't move how I expected them to, and so I'm not giving you any reward for it. And we can see this reflected in the value functions. The moment the robot misses and pulls back, it's failed the task, and the value predicted by MPR drops at that point, but VIP still thinks the robot's doing okay. So this inability to properly discriminate between successful episodes and failed episodes can explain a lot of the behavior we see with unlearning or forgetting when training VIP in this online setting. So let's come back to our figure last time. We said that visual motion features are effective for robot skill learning, and we showed how to learn a reward function from internet scale human videos using these features. And this reward function lets our robots improve their own performance without the need to manually collect a ton more data. So I think there's a couple interesting takeaways here. First of all, I keep talking about visual motion features and why they're effective for skill learning. But I also think only predicting motion of task-relevant objects was pretty key here, because it focused our learning on features that are invariant between human video and robot video. And finally, rewarding the robot for matching outcomes, not actions, helps us reduce the false positives that we see when trying to learn reward functions from human data. So, okay, let's talk about some conclusions from these works. When I look at future work on task planning with VLMs, I think there's a really interesting question, which is, what other spaces could I measure entropy in? We measured entropy in the action space for our current work, but we could measure entropy in transition space, where we look at how uncertain the planner is about what would happen if it took an action. And we can measure entropy in the cost space, which is how uncertain the planner is about how good an action is. I think it's also very interesting to measure the information potential of actual robot actions, not just visual information. So here we could try and reason about, oh, if the robot were to go open a cabinet, how much information would it get that would be relevant to its planning prompt? And finally, so far we've been looking at information gathering as an entire separate objective. But I think it'd be really cool to look at how do we balance information gathering and progress towards a goal. And this comes under many names. It's referred to as the kind of exploration-exploitation trade-off in reinforcement learning. But it also is formalized in dual control. And the very first paper I wrote when I was at CMU was this paper where we had a robot using dual control to try and both learn the structure of a puzzle while it solved it. So it was trying to balance these information gathering and task progress objectives. Okay, now switching gears a little bit to think about our word on reward learning, we've seen a bunch of really good progress towards reward foundation models that could potentially offer us reward for a bunch of different tasks all in one. We actually compared to one of these reward models, RoboReward, which recently came out. RoboReward trains an 8 billion parameter VLM to output sparse reward signals, where it will rate the performance of a robot episode on a scale of 1 to 5. And we tested their approach in simulation and found that we significantly outperform it, which I think really speaks to the benefit of learning dense reward signals for sample-efficient policy learning. And actually, when we were building MPR, I found that training these prediction models with diffusion rather than diffusion objectives rather than regression for the prediction model itself led to even better performance, but came at the cost of a lot slower inference. And because I really wanted to prioritize showing off kind of real-world policy learning performance in a reasonable amount of time, I didn't explore that for this work. But I think a lot of these limitations can be mitigated with some engineering effort. There's a lot of good techniques for speeding up diffusion and transformer inference there. So with that, can we scale MPR training to multiple tasks and to a lot of the larger egocentric data sets that have come out recently to try and make progress towards a dense reward foundation model? I think that'd be very exciting. I think there's also some work we can do to expand the capabilities of VLAs, which I've kind of been implicitly saying are less effective, but I think they do stuff very well, which is that they can perform many different tasks, but they do so with kind of imperfect performance. And normally you would have to spend a lot of time collecting additional data to improve this performance. But I think we could use MPR rewards and our reinforcement learning setup to enable VLAs to autonomously improve themselves. And we've actually seen kind of a lot of folks start to do this. The folks at Physical Intelligence have been looking at doing RL with VLAs. And I think kind of bringing a dense reward pseudo foundation model to that party would make it really work well. Okay, as one kind of last note, let's look at how we use different representations of data for the different problems that we looked at. So in task planning, I took a sequence of images and we mapped it to a more abstract representation as text. And we found that was very useful for our task planning problem, which kind of coincides with our notion that task planning is a higher abstraction subproblem in robot learning. And for skill learning, we took a sequence of images and we extracted visual motion features from them, which are kind of a lower abstraction representation. And this kind of coincides with our notion that skill learning is a lower abstraction subproblem within robotics. So I'm going to argue that we should be very intentional about what representations we use and where we use them when building a robot task learning system. And we should be hierarchical as we work towards a general purpose robot learning system. I think it's very beneficial to decompose the system into hierarchical representations so we can leverage each of these representations more effectively. And I think we should do so by following this recipe of study, feature identification, and integration into existing paradigms to make kind of consistent progress. And in 20 years, we may end up with a single end-to-end model that does all this by itself. It doesn't need hierarchical representations. But I think that studying these representations now will help us understand how to train that model. And we've also sometimes said that robotics has a catch-22 problem. We need good data to get robots out in the field, but we need robots out in the field to get good data. I think that kind of taking a path like this to build up hierarchical systems will help us get robots out there and collecting data that we might need to train our large end-to-end model one day. So the last thing I want to say is Patrick Winston, who is a professor at MIT, very well beloved by his students, said, if you have the right representation, learning is easy and everything works. So that's the end of my talk. There's some very important acknowledgements that have to be done here. First of all, to Chris, my advisor, Chris has given me incredible freedom to work on whatever I want to work on, and I am a little bit worried that I will never get this level of freedom again in my career. Chris has been an incredible source of mentorship. He has pushed me to work quickly to have ideas and to He's pushed me to work quickly to evaluate my ideas and pushed me to make sure that I can defend and back up the claims I'm making. So it's been wonderful to work with him for almost 6 years now. Rutha has also been a wonderful mentor and a friend. I am so lucky to have worked with her at Meta, and she has continued to provide me with advice and guidance ever since. I want to give a huge shout out to my committee, Chris and Rutha, but also Dave and Oliver. I was very lucky to take classes from both of you, and I've chatted with you both the whole time of my PhD, and I think you've both influenced a lot about how I think about robot learning. And a lot of my ideas have come from kind of conversations with you guys. I've also been fortunate to have a lot of great people in the lab during my time here. Ekta, Krishna, Arka, Ali, Duke, Krishna, and Iki, who I've been working with. And then I worked with some great collaborators as well. So Brian, Hamid, and Tushar helped me while I was at Meta on some of those projects. And Iki has worked with me on some work on robot learning with world models. I've also had a wonderful time in Pittsburgh over the last 5 or 6 years. Pittsburgh is a beautiful city, even though it's a little bit gloomy. I got to push for 2 buggy teams. I got to push twice for the same buggy team. And we won once. We should have won twice, but someone decided that our wheel was a 1/4 inch over the line. I've played rugby for Pittsburgh Forge. So here's me trying to take down someone who is double my size. And there's 2 of us, and we still can't take him down. But that's been a really great community outside of CMU. And we've also done a bunch of intramurals and won a few of them. I also have to shout out some wonderful friends in Pittsburgh. These friends have made my time in Pittsburgh an absolute blast. And I want to particularly shout out Abby, my partner, who has been with me the entire time of this PhD and has made everything a lot better. And finally, both in the literal and metaphorical sense, I would not be here without my family. They have been an incredible source of support. It is much easier to do a PhD when you have 2 parents who have gone through a similar process and can help you a lot. So that's an incredible source of privilege. So I'm very thankful to them and my brother and Calvin. So thank you so much. I would love to answer all the questions. We're coming back to this overview of my thesis.
Excuse me, our tradition is to start with the committee members furthest away, which is Ruta, and give the committee a chance to ask questions, and then we open it up to the audience, and then we do other things. So Ruta, you get the opportunity to ask questions.
Thank you, Chris. Good to see you all, and awesome talk, Mrinal. Really enjoyed looking at all the work together. It's impressive how long you have come, and I can't wait to see all the things you'll do after this. But yeah, okay, before that, some questions. So maybe I'll start with some specific questions about the projects first, and then some broader questions that I have for your recipe that you have sort of like built over the course of your thesis. For the query work, some clarifying questions. Query right now works with closed set of actions, right?
So this is a very good question that I didn't get a chance to talk about. Due to time, can I come back to, okay, we're just gonna keep going back until we get there. We are getting the LLM to generate a very large set of actions and then pick among ones that thinks are reasonable. And there's 2 ways we kind of looked at that. One way is to kind of do a very coarse pass to rate a bunch of different actions. So in that case, it was a closed set, but it was a closed set of like 100 actions. So it was a very large action space. So we do a very coarse pass to rate a bunch of different actions, pick the top 5, and then use those in this reasoning procedure. The other was an idea that you and I had talked about way back in 23, which we called hypothesis testing, where we would get the LLM to generate a bunch of plans freeform. So it could generate basically anything it wanted. And then we would collapse those plans into a kind of decision tree. And then we would navigate that tree. And every time we came to a branching point, we would run this kind of reasoning pipeline to decide which branch to explore. So we've kind of looked at large closed sets and what I'll consider more open sets of actions.
Great. Yeah, I was trying to remember that, so thank you for reminding me. Yeah, so I think also on that note, another question I have is right now, how many times do you end up querying? Like, do you have any analysis on like how that matches with like points where there was really ambiguity around the state or where you were in the task and so on? I'm curious if you have done such analysis, and if not, we can talk about it later.
So I cannot give you super concrete numbers on that. For the case where we're building this kind of decision tree uh, and then navigating it, the number of branching points is contingent on how many plans we generate. We cannot have more branching points than plans we generate. And often we have kind of log order fewer branching points. So in that case, okay, if we're generating 5 or 10 plans, we're going to have maybe 2 or 3 branching points. In the context of kind of considering the full actions at every step and doing it iteratively, we kind of hit a few more queries in that sense. And so for the context where we were just looking at kind of actions with 5 horizons, that wasn't a huge issue. But presumably, if we were to try and scale this up to super long horizon planning with VLMs, that might become more of an issue.
Okay, okay. For the VQA itself, there is no structure, right? Like in terms of the like what questions to ask and so on. Can you also remind me of that?
Yeah, so it asks whatever it wants. I went down a little bit of a rabbit hole on trying to get it to ask better questions. I looked at genetic algorithms that would kind of iteratively improve its question prompts over time by putting it into a simulator and trying to get it to work better. I didn't see a huge amount of success with that, but maybe there's more things to be done there. But right now we're letting it freeform generate questions and then relying on the information gain metric to decide which of these question answer pairs are actually relevant to our task.
Cool. Yeah. Yeah. I think, to my prior question, I think it would be useful to sort of like understand like whether the querying is happening where we think it should be happening, and the information gain is uh, like appropriate at places where, there was higher uncertainty or something like that. Yeah. Yeah. It would be cool to do some
Go back
analysis.
and look at that and try
Yeah.
and get some more concrete numbers to toss in the thesis document
Yeah.
about how many queries are we actually making.
Yeah. Cool. Yeah, for the NPR work, I saw that, yeah, I mean, you're mostly using egocentric videos. I
Mhm.
understand why. I'm curious if you had to use instead, third person videos, how would the quality of everything look like?
I think third person videos would be a lot easier. There was a lot of things I had to do to make ego videos
Okay.
work, including subtracting out some level of background motion. The benefit of ego videos was actually that you see so many different viewpoints that we found that this model was pretty invariant to where we placed the kind of third person camera in the robot setup, and we could move it around reasonably. I mean, maybe if it was a totally weird angle at the back of a microwave, it wouldn't work, but we could move it around reasonably and still get pretty good results. So that was nice to see.
Hmm. Okay, so yeah, okay. I thought it would be easier with ego videos because like you could actually the prediction of like how the point should be moving from your perspective, which is what the robot would see, would be better. But yeah, I did not realize that yeah that it has other challenges of like yeah. I was basically thinking of it from the perspective of the quality of reward model, that maybe it would be better with the ego video. So that's not the case, you think?
I think it's a good point. I do think we should get some benefits from ego video with the challenges that we have to predict points relative to the background, not relative to the video frame, because the video perspective is moving during ego video.
So if I could just comment,
Yeah.
Ego Video has a huge advantage that is pointed at what is relevant to the task.
Often, yes, but not always. Humans don't always look at what they're interacting with, which is kind of weird sometimes. Like a lot of times, someone will be opening a drawer and they'll already be turning to look at whatever they're about to do next. And so part of the whole object masking and whatnot helped us filter out cases where that was true. So it is true in some cases where humans will be looking at what they are and they generally don't occlude their own sight line, which is nice. But sometimes they move so fast and they do weird things because they're humans that we don't get that assumption all the time.
Back to,
Yeah. Sorry, go ahead, Chris. Did you?
oh no, go ahead.
Okay, okay. Yeah, I think for NPR, I mean, I think you do show with decent amount of context-rich tasks, but I'm also curious, if you had even more context-rich tasks, do you think this would scale? Especially, basically learning these features from just point movements. Um,
That's a really good question. There were definitely some limitations we saw. So for example, trying to manipulate very small objects that were partially occluded by the robot gripper ran into some problems. I think mainly because we just didn't have enough points to track on that to get a stable signal. So one of the things I tried to do was get the robot to like hold a knife and cut a toy carrot, and I just could not get that to work because the gripper would just occlude half the carrot from any angle, and we would not see what was going on. So that's definitely a limitation there. We could probably Chris loves talking about like kind of adding cameras everywhere and intelligent placement of cameras. And so we could definitely mitigate some of that by using multi-views. And some people have kind of upgraded this stuff to 3D, not in the context of reward learning, but in the context of action generation. So we could also get benefits from upgrading this to 3D as well.
Okay. Yeah. Yeah, actually on that note, I also want to sort of like I would love your perspective on like general limitations of your recipe and like some of the things you have built. And I mean, yeah, maybe the future work already talks a little bit about it, but just yeah, just to be explicit about some of the limitations for the approaches you have put together.
Okay, so I'll talk about three limitations: stuff specific to task planning, stuff specific to skill learning, and then some general recipe stuff. On the task planning side, we kind of operate under this assumption that the LLM has the right plan somewhere in its weights, and we just need to kind of elicit that correct plan from it. And often this assumption is not awful because with at least some reasonable few shot prompts, you can get pretty close. But certainly in cases where the LLM doesn't even generate the right sequence of actions, we can't do anything by trying to intelligently select actions. And if the right actions are so far outside the distribution that we would need to sample a ton of different possible plans to even get there, then we're in trouble. So I think that is probably the biggest limitation on the task planning side. On the skill learning side, these kind of small objects and maybe very contact rich stuff where we might be occluding things is one limitation. Another one is just access to data. So I think all the tasks I showed off had at least like 20 videos in Ego 4D, and some of them had a lot more, which worked a lot better. There's some tasks we just don't have enough videos of right now in these data sets. Obviously, there's a ton of new Ego video data sets that have come out recently, so it'd be good to look into those. It would be very interesting to look at too of can we kind of augment this with other data because this representation is kind of invariant to who's actually doing the action. So we could look at both in-domain human videos and even fine-tuning on these same robot demos that I use to kind of kickstart policy learning. In this case, I don't, but I think it would be interesting to look at that as a way to better ground this model to our specific task. Okay, so that covers limitations on the skill learning side. I think with the recipe overall, at some level, it's a fairly general recipe of saying, hey, we should spend more time kind of studying these representations and using them effectively. And so like from that perspective, I think it's an important component. I don't think it's going to solve all of our problems. And clearly there were limitations we identified that were not just inherently solved through representations. Representations were just helpful for kind of pushing us in the right direction. And there's always this kind of ongoing debate about how intuition or model-based should we be versus how end-to-end learning-based should we be when scaling this stuff. And I think that reasoning about representations, like I said, will be very useful right now when we try and figure out how to build these models and what types of data we should be using. And maybe its efficacy will reduce as we look future in the horizon, where we can kind of hopefully begin to collect data at the same scale that other AI fields have collected it.
Yeah, that makes sense. Yeah. I really like the breaking the catch 22 with this sort of like going out in the field, with like a hierarchical and a more representation rich approach. So yeah, I think then going back to the recipe question, I basically I see that you're pushing for like learning from real world data as much as possible, and I would love to
Yes.
understand the role of simulation in sort of as a data source and also just maybe as a complement. So I'm curious if you can tell me a little bit about how simulation could sort of like maybe aid or complement your recipe.
I think that's an excellent question. And actually, the very first version of this talk, I had a slide that said, okay, the three general approaches to solving our robot data learning problem are A, collect more robot data, and just kind of scale that up with stuff like Yumi that has looked at making data easier to collect. B is leverage large-scale simulation, which a lot of the folks at Gear and NVIDIA have been doing, as well as a bunch of other labs. And C is the human data approach. And I think there's a lot of very cool things we can do with simulation. The Allen Institute folks recently showed that, hey, if you just make diverse enough simulations, you don't really need to worry too much about visual, what's the domain randomization. You don't need to worry about visual domain randomization, just sufficiently diverse simulation works really well. And there's also been some work out of Abhishek's lab recently that looked at, hey, you can exploit the fact that we can reset simulations however we want to get the task into weird states and then train policy learning that way, and we end up with super robust policies. So I think we can take a lot, especially the reward learning work, if we can put that into simulation and use that to try and use reinforcement learning at a larger scale to improve upon the existing capabilities of our kind of large behavior models, including world models and VLAs, I think we could make a ton of progress in that space. The limitation is that simulation works really well for things like pick, place, open, close. As we start getting into deformables and granulars and other wacky things, we may run into more kind of physical domain gaps.
Yeah. I think especially for soft and soft fabric, or like deformable stuff, definitely sim is pretty far. Yeah. So one last question before I let others take over and ask you more questions. I'm curious how you basically divided your work in task and skill learning. It makes sense. I'm curious if you had to do both of them together for a problem out there for for example, for the Sunday demo you were showing. How would you go about doing it? And how do you put the two together?
Oh, another very, very good question. So right now I would say that I think language is the right way to connect these two. That's partially driven by what we've seen work so well so far, and that we have language model planners that predict language, and we often specify skills in terms of language. So if we say, okay, we want language as the kind of thing that joins our task planning, our skill learning, and that may work well. So I to try and do some more kind of hardware experiments, I was essentially using language as the joining factor there. And I'd love to go back afterwards and see, okay, if we pair a VLM task planner with all the kind of creative promptings we've done with a VLA that should have some language generalization, though it might be limited, how far can we actually get? Beyond that, I think there's a lot of very important questions to try and propagate information up and down this. And so from there, language could be a bottleneck. For example, if something goes wrong at the skill level that the planner has to reason about, we either have to convert that to language somehow or get the planner to kind of observe that through vision and then reason about it in its frame. So there are limitations there too, but I think that's a very fruitful area of exploration.
Yeah, I mean, I think particularly when something goes wrong, whether that's the skill module's problem or the task planner's problem, I think that's something that's definitely been on my mind. So I would love to chat more about it with you
Yeah,
later.
absolutely.
Yeah. Thanks. I'll let other committee members chime in now. Thank you so much.
Cool.
Thanks a lot, Ruta. Oliver, you wanna go?
Yeah, thanks for the presentation.
Thank you, Oliver.
A lot of great work. I'm also gonna go a little bit from details first. So for the query one, I was wondering what kind of questions does it actually ask of it? Because you mentioned this example of the VLA with the toilet being white.
Yeah.
Then it works and it doesn't look white, but that's as a human you wouldn't really.
Think about that.
Well, yeah, that wouldn't really change my interoperability actions, right? So is it actually sort of selecting things that are oh yeah, makes sense from a human perspective, this is important relevant stuff, or is it helping the network just become more certain, but it's actually sort of more the nuances of the network?
That's a good question. From what I've looked at, I think it's more of the former. I haven't seen a lot of case. Well, actually, no. I've seen some small cases where it'll ask something that I think is not relevant, but we do see a large change, and that kind of I think actually that's another important limitation.
Yeah.
Ooh, So in this, like sometimes it'll say where is the lettuce, and the lettuce's location has no bearing on what to do next, and that gets reflected properly. I'd say 95% of the time that gets reflected properly in the probability updates. But this was more true with older models when I was testing this with Llama 3.2. With Quen 3, I've seen a lot less of this, but sometimes we get questions along that variant that I can't really do. Sometimes it asks really bad questions like, oh, what should the person do next? And it's going to say, oh, you should do XYZ. And the model's going to be like, oh my God, that's such a good thing to do. I'm now very certain that I should do XYZ. And so even though that was totally uninformative and totally driven by hallucinations, we saw kind of a probability collapse there. That happened a lot less when we moved to Quen 3 models, and it happened a lot less when we kind of ask it to do some thinking and some chain of chain of thought reasoning before it generates the question. So there's a bunch of prompting tricks we can do to reduce that, but certainly that's a limitation there.
So for the preference learning part. So first of all, does it like for like the optical flow and stuff like that? Does it adapt to like target objects that are stationary? Like if you have like putting things on a coaster and the coaster might be different locations. Or, like it seemed like the wiping was kind of always the same location, for example.
That's another very good question. I didn't look at too much pick and place here. But one thing I did see was, okay, for things like wiping and folding, they're ambiguous tasks. You can't fully specify the task from just saying fold the towel. And what we'd see is that the kind of predicted point motion vectors were pretty random before the robot touched the towel. But the moment the robot picked up a corner, suddenly they all collapsed to say, hey, this corner should move to the other corner. So there was certainly some ambiguity at the start, but once the robot did enough to resolve the ambiguity, then the reward took over really nicely and got you all the way there. So, and part of that is that if we have to initialize with some base policy, we can't run this from scratch because then maybe we'll never get to that point. But we do see this behavior that once the ambiguity is resolved, it suddenly collapses. I didn't test it too much with like pick and place though, so it might be interesting to go back and look at that.
So point of clarification. When you're using the visual motion features, are you also using other features as well?
The prediction model takes in the full scene image and the query points and tries to predict how they're going to move for the next frame. The reward computation is using just the predicted point motion and the observed point motion and diffing those to get reward. It's not looking, so the reward computation only looks at the point prediction, but the point prediction model gets to look at the whole scene and go from there.
Okay. Oliver?
All right, so I mean, I feel like you put a lot of emphasis on the sort of the Socratic model versus the vision condition model. It kind of seemed like the Socratic model kind of came out ahead of it. And I'm kind of wondering, like, is there not a hybrid between these, right? I mean, I think in your like the template selection, you kind of said like the pure LLM was like 2/3 of the times corrected.
Yeah.
Right. So like, I can see that as like being a very strong prior, for example, and then, like having a completely, no vision system also seems kind of weird.
Yeah, so that's very, very true. And practically what we did because we had a library of like 30 or 40 controllers and we didn't want to run all of them in the real world. So we would get the LLM to give us like top 5 controllers it thinks might be useful for this, and then run the vision systems on top of that. So that's kind of doing this 2-stage scenario where the LLM is acting as a quick coarse selector and vision is acting as a slow fine-grained selector. And the fact that we are seeing, especially with the flow encoder, boosts on top of the LLM performance means that, okay, the LLM is giving us a reasonable prior for what we can use, and then vision is actually giving us good incremental benefits beyond that. Does that answer your question, Philip? Yeah, okay.
I guess there's other ways to kind of think.
Yeah. I think that at a higher level, there are a lot of synergies there where language does very good quick coarse reasoning about general applicability, and vision does very good slow fine reasoning about specific applicability.
Sampling disorders.
Yes, exactly.
So for the evaluation task, right? Like I feel like you focus on location domain and location domains, but I do kind of wonder, like to what extent do these algorithms, these results generalize to other tasks, right? If I do like Lego or like Lego technique assembly, right? Is it really still going to be that like the Socratic model is better? Yeah, like I'd love to know more about sort of like how you chose like the task and like what are the tasks where this starts breaking apart?
That's okay. It's a very good question. when I start, so if you talked to me in 2022, I'd have been like, oh my God, kitchen domains are great. Like we should be studying all of this. They've got, they're very relevant to what humans will need to do, will ask our robots to do. They've got a good variety of objects. They've got deformables, they've got granulars, they've got breaking contact and all sorts of crazy things. Kitchen domains are very hard. It is very hard to get a robot to manipulate food well and also very wasteful of food. So you want to be very careful about how you do that. So that's why kind of on some of my last projects, I stepped away from that to look at tasks that I would say are more typical with other folks in robot learning do. I think one benefit of kitchen domain and those similar things is that they are tasks very well represented in our human data. So LLMs know a lot about cooking. Epic Kitchens was kind of one of our first big egocentric video data sets. So from that perspective, I'm certainly matching my domain a little bit to where my data comes from. I think, so on the task planning side, as we get further outside the domain of what people have talked about on the internet, we kind of lose performance. So if there's 101 recipe websites that will tell you how to make something, but for a very specific Lego assembly, maybe we don't know as much about how to do that. And intuitions about how to build Legos may be less textually documented on the internet. So certainly the further we move outside our distribution, the less performance we get there. On the skill execution domain, I think it's also another question of what videos do we have of people doing things. Now, specifically in the Lego domain are things that involve a lot of fine-grained closed actions that are very kind of dexterous. Vision approaches, especially kind of single camera vision approaches, will have a rough time. And we'll need to think about kind of more rich representations, including tactile sensing. And a lot of folks have done very good work there. I had a second point and I totally forgot. Talking about skill learning. Okay, I'm gonna say, if it comes back to me, I'll say that. But I think that certainly we benefit from being kind of in domain what our human data is. And if we step out of that, we're gonna run into problem. But I'd also argue that for at least home robots, a lot of the things we want our robots to do are kind of in domain of where our human data is as well.
All right, I have one last question. So, kind of, what Chris said about teaching old dog new tricks, I feel like there's also the, everything old is new again, kind of, and like your recipe that you kind of present, I mean, it's like, okay, if you have the right representation, it's a lot easier to transfer from like, humans to robots. And I feel like this was something that you also like discussed during, when I was a PhD student, and like, I mean, now sure there's LLMs and VLMs, but I'm still trying to understand, like, beyond the actual methods, like, are there sort of core insights that you kind of explored now that haven't really been able to be explored before LLMs and VLMs? Or is it, very LLM, VLM focused we're looking at right now? If we get something beyond that, are we gonna, have to redo some of these things to kind of see, or, yeah?
I absolutely think you're totally right in that some of the stuff I presented here is specific to the capabilities we have now in terms of not only LLMs and VLMs, but diffusion models, whatever policy learning we can do right now, whatever RL we can do right now, it's grounded in our current capabilities and what other folks have given, other folks in machine learning have given us the field of robotics. Building on that, I would argue that if we want to be very adaptable at robotics and we want to keep leveraging whatever things come out of other fields that have and kind of build on their insights, taking a very systems focused, let's deploy this and study it and analyze it on tasks that we consider to be representative, I think is maybe the most effective approach we can use. Because if we're taking data that's out of domain and trying to use it in our domain, we need to do a very good job of characterizing what it is good at and what it's not good at. So while I think that the specific instances of these here are kind of stuff that works well in the moment and will certainly be eclipsed in a few years as people kind of develop better methods. I would argue that this approach of taking what other people have built in adjacent fields and trying to run it on robots, seeing what happens, analyzing that, identifying what representations and which models specifically work well for our different domains, and then trying to build on that is a generally extensible approach.
But would you say there's like key insights that you gain now from working with VLMs that are sort of beyond VLMs?
I would say in that context, I think if you want to, I think there's some level of representation matching here. If we want to reason about very high abstraction sub-problems in robotics, which is like, okay, I need to predict a long series of actions to solve this. I'm going to generally benefit from upgrading my data into higher representations, regardless of what I'm actually using to do that change. VLMs and LLMs are very useful here because they can kind of serve as universal I/O. They take in a lot of different modalities and map them to language. So from that context, I would say that some level of being cognizant about what is our target representation that we want to use, what representations our data come from, and how do we kind of get it to match that is generally useful. I don't know if that answers your question. Okay.
David?
Great, yeah, really nice talk, and great work. I'm gonna start with some specific questions and, yeah, so, for the second project, you mentioned, that you could use diffusion, to get even better performance, but it's a little bit slower.
Yeah.
So can you explain more how you would use diffusion?
Yes. Let's go over here. I'm gonna go. Okay, so when we get to this part where we are trying to train this, right now I'm just like regression, taking query points, predict how they're going to move.
Sure.
You can do the same objective but with diffusion. So
Right,
actually,
right.
and there instead of just predicting one step, like usually we like to predict a couple steps and then just use like one step. But you train it with that same
Yeah,
idea.
so I guess my question is, so diffusion is a stochastic model. Every time you run it, you get a different
Yeah.
output, right? So how do you take that distribution of outputs and get a reward from it?
So diffusion should, if trained well, kind of converge to a similar point motion. And it may be kind of multimodal, and at some level we want that. Multimodal, not in the like sensing modalities, but in the kind of probability sense of multimodal. Because when we look at like going back to Oliver's question, when you look at tasks that are fundamentally ambiguous, they have a bunch of different ways you could do them.
Right.
And so at the start, we have to pick one. Right now, actually, regression kind of hurts us because it just kind of averages all the different ways you could do it, and you end up with noise.
Yeah.
Diffusion, when we saw, actually will kind of commit to one of those modes,
Right.
and then once it switches, then it'll suddenly flip to the other mode.
Yeah,
as it
I
goes.
guess my question is, so let's say that you're computing rewards, the
Mhm.
robot took an action, right? And let's say it took action A1.
Mhm.
And let's say that A1 is one way to do the task, but A2 is another way to do the task.
Yeah.
So you run your diffusion model, it gives you a prediction, maybe it predicts A2, but your robot took A1, so then it gets a low reward, or like how would you address this issue? Do you see what I mean?
Yeah, I see what you mean. That's a good question. I could say practically, if you're like from what I've observed, if you're doing the same actions every time, you should get a fairly consistent motion prediction. If you're seeing the same states, even though diffusion is kind of initialized randomly, that at least if diffusion's trained to convergence, which certainly takes a while, it still kind of seems to collapse to similar predictions if it's seeing the same states. I didn't see a ton of variation. No, I think if you do like small jitters on the states, maybe you can see.
Sorry, so actually, let me break my
Yeah.
point down into two separate things. So first of all, you're looking at opening microwaves, right?
Sure, in this one, yeah.
Yeah, did you look at other tasks or?
So, I mean, I have stuff for like cloth folding and wiping, which are less specified tasks.
Right.
Yeah.
So for opening microwaves, you saw a benefit with diffusion even on this task? Or?
Yes.
And so I guess okay, so let me just start with that. So I'm sort of surprised because this is not a multimodal task in the sense of having multiple ways you could open a microwave. Like the microwave motion has to follow a very specified kinematic trajectory. So why do you think diffusion helps even in the microwave task?
I think in the microwave task, the improvements are a little bit more muted.
Okay.
I think that the primary thing you're getting there is you're not getting this kind of smearing effect from regression, where if you have small variations in motion, regression just kind of tries to predict the middle of them. And will sometimes, I mean, like concretely what I observed is that you get more kind of wonky vectors when you do regression than diffusion. You can try and discuss why that is, in addition to kind of multimodal representations. Diffusion does its own data augmentation at some level and can sometimes get more stable predictions. So that might be part of it. Even the microwave thing, which is pretty well represented in the data set, is only, I think, about 100 videos. So that's not a gigantic number of frames.
Right. Okay, so maybe in this case, the reason is not because of multimodality, but just that
diffusion works nicely. Yeah.
Diffusion, yeah. Okay, now let's take another example. Hypothetically, let's say I'm trying to like push this pen,
Yeah.
around this thing. I could either go this way or I could go this way, right? So you run your diffusion model and it shows vectors pointing in this way, right?
Mhm.
But then the robot takes an action to go this way, so you would get like a bad reward for that.
Yes.
So how would you like address that?
So that, yeah, it's a really good point. So when you're at the very beginning and you haven't picked a direction, absolutely, it may this time say, hey, you should go left, but you went right. So you might get bad reward for that step. But once you commit to a direction,
Sure.
then the distribution collapses and says, okay, you should keep going in this way. So certainly when you're kind of in that state of ambiguity, maybe the very beginning of the task, you'll get wonky rewards. And part of that is actually value learn, like Q function learning helps you a lot here, because even if you have intermediary predictions or like intermittent predictions that are bad, Q function learning should kind of smooth them out and do a good job.
Right. So I guess this thought experiment leads me to think that at least the way you're currently doing it, the multimodality of diffusion actually hurts you, but the accuracy of diffusion is the thing that helps you.
Oh, that's a good point. Maybe yes, but also in this case, regression would predict that you should just go straight through the laptop, which would be wrong in a different way.
Right.
So it may hurt you at some point, but I think the magnitude to which it hurts you is pretty minimal compared to the benefits you get from generally more robust predictions.
Right.
Yeah.
All right, cool. Great. So let's see. Yeah, that was my set of questions on that one. For the first project, I guess, oh, sorry, do you serve these object masks? Is that from like Grounded Sam or something?
I used a wacky combo of Owl VIT2 plus SAM2 and then QD to track masks, just because I'd used that before and it worked well.
And you're prompting it with the language,
Just, yeah.
the object.
I just pulled nouns out of the task description and then said, hey, go find these nouns. And it worked. I mean, it works really well on the robot video that is kind of higher resolution and higher contrast. There were about maybe 5% errors on the ego video, but I didn't manually correct for them, and the network just kind of overcame it, so that was fine.
Right. What happens if you don't have object masks and you just track every point?
Good question. I've got backup slides for that. Which is this ablation. Okay, it's not great. And the reason it's not great is because we get kind of closer to VIP levels of bias. So we do benefit a lot from saying, part of this is if you don't do object masking, you can't do background subtraction. And I actually saw that we were overfitting a lot quicker when training the motion prediction model, because it was kind of like fitting to weird things in the training data, and then it wouldn't generalize nicely to the validation data. And so one, you get kind of worse training, and two is you get this much more biased reward representation. We still see that we're doing the task, but a lot of this noise here in the beginning will hurt your learning performance.
Just so I understand. So in theory, you should just predict zero motion for the background. And then it should be fine.
Yes, you should predict zero motion for the background. I do in ego video training, I kind of use the object masks to identify what's object and what's background, and then compute a average motion vector for the background and subtract that out. But when I train, I actually still do. So we found from a lot of the point tracking models like CoTracker that they benefit from having other points to track around objects. And the whole point of CoTracker is that you should track all these points together.
Yeah.
And so when training the model, I actually do kind of a weighted sampling of object points and background points. So I'm still sampling a couple different background points even after the background motion has been removed, to try and encourage the model to predict object motion relative to whatever background motion.
So that makes sense. I guess I'm asking more about this ablation where you don't have a mask.
Yeah.
I'm trying to understand why removing the mask hurts so much. I would think that I guess I'm sort of surprised it hurts this much, because at least in theory, CoTracker should just predict zero motion for the background. Your motion predictor should predict zero motion for the background. Is the reason that CoTracker does accidentally predict motion for the background, or your motion predictor predicts motion for the background?
I think the issues are not on the execution side. I think they're on the training side. So on the execution side, you're absolutely right. CoTracker is going to predict no motion in the background, only motion for the objects, and we're fine. But on the training side, I think we're grabbing a lot less of the salient features from the the ego video by having to learn to predict all the background motion in addition to the object motion. When we say that, hey, you should,
Motion predictor
yeah,
actually ends up learning mistakenly to predict some.
spurious correlations in the background rather than what we care about, which is the object motion.
Okay, interesting. So in that case, I guess I wonder if you could treat it more like a soft mask that guides your motion predictor to say, like there should be no motion for the background, but we might be wrong about the mask, something like that, as opposed to like a hard mask that you apply.
That's a good question. I think we get part of that by still sampling some background points during training and eval,
Right,
but maybe not the full thing. Like you could basically add a loss function or a penalty saying that you shouldn't. We'll allow some background motion, but really there shouldn't be that much.
right. Or like if it's just on the input side, I guess it seemed like from your network, you're inputting the mask to the network.
Sorry, okay, that was a little bit of a misnomer. Yeah,
I see.
it's we're inputting the query points are primarily on the object with
Right.
some background points sampled.
Right.
Those are the inputs, and we predict how they machine.
Okay, you could input the mask directly.
Yeah, you could. I mean, maybe if you're really scaling this up, maybe you can get it to predict its own masks,
Right.
but that's not
That's
needed
like-
for this level.
Okay, great. Okay, so on the first project, so yeah, I really like the direction you took. I was wondering, how you think your model would handle a particular example that
Mhm.
I have explored in my own work, which is, imagine that let's say you're packing a box, you have one object that's kind of in the middle, and then you're trying to put a second object, and you need to know, do I need to first push this first object out like to the side? Or can I just put the second object next to it? So you sort of need to kind of reason about like, is there enough room next to the first object to place the second object, right? And it's sort of like a very visual thing of like how much space is there, that if you just sort of naively transformed this image into text, it would say there's an object in the box, and that's it. But what you want is there more details about like, where is this object in the box? How much room is there next to the object? I feel like your method might actually be able to handle this through the I forget what you call it.
The question answering?
Yeah.
Yeah, so
What do you think?
in the ideal case, the question we'd ask is not, is there an object in the box,
Right.
but how much space is there in the box?
Right.
And
something like that.
And we may have trouble just answering that purely from vision because spatial reasoning can be hard.
Sure.
But like, so Gemini is trained these kind of embodied reasoning methods that are supposed to do better kind of 3D reasoning. And certainly we could think about augmenting this visual question process with tool calling as well, where you try and do a little bit more specific reasoning about
Right.
how to answer this question in a more concrete way.
Yeah.
So I would say the general framework can hopefully address that, but maybe we're not in this exact form.
Sure, yeah. Okay. Anyway, I really like it because I feel like most frameworks could not address that, but yours like kind of is pointing.
I think we can make progress there.
Yeah, that's great. Okay, yeah, I'm good. Yeah.
Cool. Chris.
I've been messing around with VLMs. And I've been surprised how bad they are.
Mm-hmm.
I had a broken suitcase, the wheel broke. I took some pictures of it. I showed it to ChatGPT. The language part perfectly identified where the wheel was. It made some other mistakes. This is all from the picture. Then I asked the VLM, put a mark on the picture where the wheel is. It's totally in the wrong place. I guess that leads me to ask the question, are VLMs just not ready for prime time yet? And should we be using them in a different way than tying them to language? You mentioned the problem that all these multimodal large models don't know a priori what weight to give language, vision, sound, touch, any other modality. It seems to be VLMs hurt rather than help.
I think that's really good. And in the context of vision reasoning, at least for task planning, a lot of the works have used explicitly vision API calls where you get information back as numeric values like, oh, your object detector says your wheel is right here, rather than kind of these freeform queries. The freeform queries have mostly been explored in the context of like VLM reasoning for more like kind of computer vision language data sets, but less so for like embodied action. And I think part of the reason is exactly this, that it can be challenging to represent all the things you want for embodied action in the context of language. And so certainly, at least with where we are now, we'll probably derive a lot of benefits from using some of these purpose-built vision APIs that have been designed to solve specific problems we care about in embodied reasoning. As we go forward, maybe that will change. Hopefully that'll change, and that all these models will just kind of operate within one, and I can say which pixel is this on, and it'll tell me which pixel it's on. I can say, give me a depth map for that, and it'll give me a depth map, and I can just use that to say, okay, here's where in 3D location I need to go. Right now, it's not a capability we have, at least perfectly. It'll happily tell me which pixel it's on, but that might not be correct. So I think we still definitely see some benefits from using some of these more purpose-built models that can give us more specific representations than language. But I mean, you can use language to represent a lot of, like, language doesn't exist at a single granularity, right? You can have very abstract language representations that just say, oh, the wheel is in that corner, or you can have very specific language representations that say the wheel is right above the white mark on the bag, and it looks like this.
Yeah, I'm sort of realizing in your thesis, you address selection of what are called primitives, subroutines, or whatever you want to call them. But you did not address computing the appropriate arguments for those subroutines, which would be the location of Oliver's cup, for example. If I reach over here, I'm doing the right primitive, but I'm not grabbing his cup.
Yes, absolutely. When I started the PhD, I was very excited about like kind of reasoning about primitives and how can we learn primitives and arguments for that. And I spent a little bit of time looking at that. In some senses, I've been surprised we haven't done more of that as a field. I remember there were some papers that came out in 2022 that were like, hey, RL works really well if we just use kind of parameterized primitives for RL plus some like freeform action. We can do a lot of stuff we thought we couldn't do before. But when we've kind of moved into this large behavior model era where we try and train a bunch of behaviors into a single model, we've just kind of treated these behaviors as discrete things to be selected by language without doing a ton of, I mean, the parameterization might be, oh, pick up the green cup versus pick up the blue cup or whatever, but like we don't have a specific way of saying, oh, pick up the cup that's located at XYZ position right now. I mean, and so VLAs have done some of that, but we also see that it can be kind of fragile where some descriptions or some parameters will work well, some parameters will not work well, even though we would assume those parameters should encode the same value.
So I would argue that in general, the testing of the vision component of all this has been inadequate because the environments are so impoverished.
We do tend to work on a lot of very clean environments where there are the task objects we care about and not much else.
That is also a criticism of your try 3 different, wiping, the other thing.
Yeah.
The other thing. Those were basically the same environment over and over, visual environment, essentially pretty much the identical image over and over.
Yeah, I should go back and add some distractors there and see. Now, I think in my case, I might fare a little bit better because I am doing specific object masking, and I'm relying on these open set object detectors that are pretty good, and they sometimes actually they often impress me with how good they are at finding things in clutter. So I might kind of benefit a little bit more from there, but I should certainly go back and run that test.
Okay, let's open it up to our wonderful audience here. They're very patient. Anyone have a question? Come on, people. Yeah, in the back.
So a task formed by a highly proficient human is completely different than a novice. Easier to learn from novice task performers first, and if so, are we teaching non-efficient tasks models?
That's a really
When I'm slicing an onion, I'm pretty novice doing it. But if you train your model using my task, you probably get a bad model for onion slicing.
That's a very good question. Yeah, I mean, we talked a little bit about kind of, oh, humans don't look at what they're doing, and it's especially true when they're really good at what they're doing is they don't look at it, which kind of throws a wrench in our plans. And so certainly at some level, yeah, I think it's probably it's a good observation. It's probably easier to learn from people who are not hyper proficient because they may be employing strategies that are harder for us to do. Um, Chris and I have chatted a lot about how do you characterize different strategies for tasks, and your strategies may certainly evolve as you become more proficient. Um, so to answer your question, I might say yes, we are like right now, if we have to learn from, I mean, I think this certainly depends per task. Some tasks we can learn from a whole variety of strategies. Some tasks we see a clear benefit where certain human strategies are easier to learn from than others. And I could certainly accept the argument where, oh, sometimes this is correlated that the strategies that are easier to learn from are the ones that are maybe less high throughput. So in that sense, yes, we might be benefiting more from suboptimal performance. I think that's a problem that's kind of endemic to robot learning as a whole right now, where robots are slow and clunky, and even our kind of a lot of our best pick place models are still running at like a third of the speed of a human doing the same task. So I don't know if I have a perfect answer for you there. Certainly, some aspects of better sensorizing our environment and getting access to more relevant features may help us to identify the minutiae that make more complicated strategies work well.
Other questions, thoughts, comments? Okay, one last round of applause.
Thank you.
Now we do our secret stuff, which means you guys go out and have a chat. Have Mrinal, you, kill recording and get everybody up off the thing except you guys.
Okay.